Hello, everyone. I'm starting the presentation. I think we are running a little bit late, and so I need to catch up. So this is Ruggero Poletto, and today I'm going to talk about artificial intelligence prediction of FDS fire scenarios. So we are all familiar with FDS. We run CFD simulations with that. The standard approach in FDS is that allows us to simulate a fire scenario, and it allows us to give us some guidelines and some engineering advices on how we have to design buildings. Obviously, in order to do that, we have to actually execute simulations. And we know that sometimes simulations can be very expensive in terms of hardware resources to use to get results. And this gets even worse if we consider that the regulation sometimes forces us to establish the worst case scenario in a car park, in a warehouse, in a building, and to make the evaluations, to make our considerations in this peculiar case. So we need experience, or we need a lot of simulations, just to understand where is the worst case scenario, where we have to locate the fire inside our building. And for this, my idea is to use artificial intelligence in order to do two things. One is to make predictions. So instead of running a complete simulation, we can submit first our input FDS file to the artificial intelligence to get an estimate of what the results of this simulation can be. So we can get these results a little bit in advance to understand if we are actually simulating the worst case scenario or something that is not the worst case scenario. Obviously, this is a prediction. It's not really the results of the analysis. We will still have eventually to perform the simulations, but it can be like a quick way to know where our simulation is going to go. And the second thing we can do with artificial intelligence is getting guidelines. So the artificial intelligence, given like the floor of an indoor car park, can actually estimate in which places can the worst case fire scenario be located, and consequently can help the engineers into making the decision of simulating the worst case scenario. Again, these are guidelines. It doesn't mean that the artificial intelligence will tell the engineers where to locate the fire scenarios, but it's another instrument that can help engineers in doing their fire safety activities. When using artificial intelligence, we need to have some hypotheses or requirements that we have to make to the artificial intelligence in order to reach the results. Well, first of all, artificial intelligence has been coupled in a very good way with other CFD software, but always to estimate steady-state results. In our case, most of the times we're not interested into steady-state results. We are interested into the transient behavior to reach, let's say, the final steady state, and how long the smoke will take to fill a building, or how long we can keep our temperature to an acceptable level inside the room. So we need to implement some level of transient analysis. Another hypothesis is we can just simulate localized fire. In FDS, when performing a simulation, you can let the fire spread across your warehouse, okay? In this case, it gets a little bit tricky for the artificial intelligence to do that, so we keep it localized. The fire starts and finishes in a predefined area and cannot expand to any area nearby. We can predict like all the variables in theory, but I'm limiting the prediction to the smoke visibility and to the temperature inside our building. And it would be also nice to have some sort of accuracy report, like the artificial intelligence would be nice if it could give us, this is the predictions, and I expect a 20% accuracy in this sort of predictions. And also the results will be only qualitative, okay? We cannot get like devices that are gonna get into an Excel file, but we can get qualitative report of the simulation. For those of you that are not familiar with artificial intelligence, you need to, before making predictions, there is another activity which is fundamental, and this is called training. Basically, artificial intelligence can make its prediction only after it has seen a certain number of results of simulations, and using like a database of previous analysis can make predictions on a new one. So this activity is called training, and involves like generating a database of simulations. A database must include like the main variability of simulations, and this has to be done a priori. The training activity is quite computational resource demanding, as like in our example, for every case provided in the training activity, the artificial intelligence had to train for 1 hour. So it can get like quite complex to provide a high number of training cases to the artificial intelligence. And then once the training activity is completed, we can use the artificial intelligence to make predictions. What you need to make predictions is just the input FDS file. Okay, and you get basically an estimation of the results of your simulation. In our database of the simulation that we had to provide in order to complete the training, we have to provide the artificial intelligence with some level of variations or variability, some like various simulations. And simulation can vary because you have different geometry. So you can have a tall building, you can have an indoor car park, a warehouse, you can have shops, and within like shops you can have several shapes of the building, and all this variability should be like somehow provided to the artificial intelligence in order to understand how represent several types of geometries. You can have variabilities in terms of ventilation. You can have natural ventilation in buildings. You can have duct extraction system. You can have jet fan system. So there is a variability in terms of ventilation. You can have a variability in terms of where is my fire located inside the building. And eventually you can have a variability in terms of the S.R.L transient curve, which is imposed to the fire. These are not all the variations you can include in an FDS analysis. There are many others. There could be the presence of sprinkler. There could be fire propagation, as we said earlier. There could be a chemical reaction or different suit of CO yields produced by the fire. There could be also a geometry variation in time. Often, like in simulations, we have doors that can open or close while the simulation is running when they reach several thresholds. You know, the variations can be many, and if you also think about the numerical variations of your simulation, sometimes newer version of FDS includes new features, which can, let's say, induce like more variations. You can like vary the time step, turbulence models. I mean, there are several parameters that can vary and can make our database of simulation to provide the artificial intelligence really huge. Let's go to the training and let's see how we did that. Well, we started in a very simplified way. We chose a staircase, a simple staircase scenario, where we have a fire located in a certain place within the staircase, and we have the stair ramps, and eventually at the top we have like an openings for the natural ventilation of the staircase. The case that has been used is relatively small in terms of number of cells, so 64,000 cells were used in this particular simulation, and we used FDS 6.8, which was available in that moment. Simulations were performed on 8 cores. So we had to split the mesh in 8 cores in order to reach a good scalability. I think most of you are familiar with that. For all the simulations, we performed, we used 4 slices. Okay, we had 4 horizontal slices at several height from the floor, so 1.5, 1.7, 1.8, and 2 meters from the floor level. And we also had 2 vertical slices aligned with the X and Y axis. And these are going to be used for comparison of the results. In terms of ventilation, we didn't have ventilation. Actually, there is always ventilation, but there was no mechanical ventilation. There is just natural ventilation. Mesh size, as I said, was about 8 meshes, each of which had 8,000 cells. So altogether it was 64,000 cells. And time, that's important for the transient behavior I mentioned before. So the total simulation time was 1,800 seconds, and we sample data every 300 seconds. Okay, so that was used as a sampling for the training, and eventually the artificial intelligence is going to be able to reproduce only the sample time steps. So I'm sampling at 300 seconds. I cannot ask the artificial intelligence to make a prediction at 150 seconds. Okay, the artificial intelligence is going to be able to generate the results and the predictions only at the times I provided that during the training. And then there was like some work to do about the data conversions. I considered VTK a more easy to use data to convert. So every FDS analysis had to be converted into VTK file format for the training of the artificial intelligence, and also the artificial intelligence has been instructed to reply to us in VTK file format. So the predictions, eventually results, were in VTK file format. In order to do all the implementation to make this system work, 2 companies were involved. The first one is Navasto, which provided obviously the artificial intelligence software. They have an in-house artificial intelligence software quite commonly used in automotive CFD results predictions. And they had to develop, and actually we developed that together, a pseudo-transient behavior, because as I said before, generally artificial intelligence is used to make predictions in a steady state results for the simulations, and so we had to develop a pseudo-transient predictions. And then obviously there is my company, Cloudis PC by CFD Service. We performed the FDS cases. We had the computing power both to run the FDS analysis, to make the training to the artificial intelligence, and we also developed all the data converters from FDS to VTK file format. Among the 4 main variabilities that we mentioned before, we decided for this, let's say, first implementation to limit the situation a little bit. So we didn't include the geometry variations, so the geometry remained fixed in the training provided to the artificial intelligence. We didn't inserted ventilation variation, so we always have natural ventilation in our simulation. We included fire locations, so as a variation, so we set the fire in different locations within the staircase. And we included also HRR curves variability in time. So we simulated 2 or 3 variations of HRR curve. In terms of fire locations within our geometry, well, we set several file locations inside the geometry. 4 of them were at the ground floor, at the bottom level of the geometry, and a couple of them had a fire like after a couple of ramps and after 3 ramps. And we also made a variance of the area where the fire has been located, so we varied the area, even if the total HRR produced by the fire will remain constant. Okay, so obviously means that we are varying a little bit the HRR per unit of area in the 2 cases to have like the same HRR in both cases. Instead, for the HRR curves, we used 4 different curves. One is in blue, so they all started at 0, and the curves had a variation in terms of T alpha, so the speed required, the time required by the fire to reach its maximum value. And then they all slow down in a similar way. Altogether, we defined 24 different cases, so 6 variations in fire locations and 4 variations in fire HRR curves. You can easily imagine that having like these very little variations, we already were like with 24 cases. If we are going to introduce geometrical variations and also ventilation variations, it's easy to get to thousands of files just to provide the training for the artificial intelligence. Out of these 24 cases, we had to divide them into 3 groups. 18 cases were used to make the real train to the artificial intelligence. 4 cases have been used as testing. So the artificial intelligence, while doing the training, from time to time tests its own prediction to evaluate if the train has been sufficient. And so let's say overall 18 plus 4 makes 22. So 22 cases have been used for the training of the artificial intelligence. 2 cases instead were not passed to the artificial intelligence, were completely ignored by the artificial intelligence, and were going to be used by ourselves in order to make to evaluate the prediction the artificial intelligence was doing. And eventually we get to the predictions. So we start with the smoke visibility. In here we have on the left-hand side the FDS results of the simulation, and on the right-hand side we have the prediction made by the artificial intelligence. This is a time variance. Okay, is a transient analysis, and what we can see is the variation every 300 seconds up to 1,800 seconds of the simulation. Overall, in this case, the prediction was, I would say, qualitatively quite well computed. So it's difficult to say which one is computed and which one is predicted if someone didn't know. Even if, let's say, if we just measure every single cells, we can notice that there is some slightly difference between the predictions and the results of the FDS analysis. A similar results has also been achieved in terms of temperature estimation. In here I have just the results of temperature after 300 seconds. We can see that the differences between, there are some differences, let's say, in between the actual CFD simulation and the prediction. If you can see, like in here we have a little plume of temperature, which in here is estimated to be a little bit more moved to the right-hand side from what I can see. Okay, but again, qualitatively I can see that the temperature is mostly blocked by the first ramp, and we have a little plume going upwards, which is also can also be seen in the estimation. Again, qualitatively the results are captured, but there are some differences within some, let's say 10, 15 different percentage point, I would say, of error in the predictions between the prediction and the FDS analysis. Just to say, I don't know if I mentioned that before, but once the training activities has been completed, to get the prediction from the FDS file is basically instantaneous. It's just a matter of few seconds, and the artificial intelligence was able to provide us the VTK file, which can then be opened to compare the results. I also compared the results in terms within the slice. This is also another little exercises I did. In our case, the mesh was rather coarse, and I was able also to modify the mesh course, the cell dimensions in the artificial intelligence to create a smoother results in the artificial intelligence. That was just a game which is allowed when making prediction with the artificial intelligence. And this instead is the vertical slice, where again, after 300 seconds, let's say, most of the feature and qualitative, let's say, data of the simulation has been captured by the FDS analysis. I could proceed on and on by showing other picture. Again, this is the temperature in the 2 vertical slices along the X and the Y plane, and we are comparing this time the temperature after 600 seconds. Again, let's say mostly the area where the temperature reached a certain level is captured correctly by the artificial intelligence prediction, and this is the same variable temperature, but this time after 1,200 seconds, and again qualitatively it's difficult to distinguish what's a prediction from what's the results of FDS analysis. So the conclusion from this first work is that yes, artificial intelligence can predict at least the main features of our FDS simulations. It is important, though, the generation of wide database of simulation. In our case, the database we produced was, let's say, relatively limited, and we were able just to predict staircases, basically. I couldn't predict anything else beyond that. And once the predictions are working, it's easy to expand the prediction capability of the artificial intelligence in order to define guidelines for engineers to be applied in running the simulations. Obviously, there are some work to do in order to expand this tool and to include more capabilities. One of the biggest problems is managing bigger mesh size. Okay, currently we were able to train artificial intelligence just on a case which was 64,000 cells, so relatively small, and managing bigger mesh size is like a big challenge. And we have to include the geometry variation. There are some possibility and some algorithm that allows to do that has to be implemented as well. And then there are a couple of questions which I want to make to the whole audience. One is, in terms of output, what would be the best output to provide? In here, I was able to provide the whole domain in VTK file format, but in theory, it is also possible to provide output in terms of images, in terms of slices, but it would be nice also to know where to place these slices, where it would be more sensible to place these slices in order to get familiar with the information provided by the prediction of the artificial intelligence. That's everything. Thanks for listening. I'm ready for the questions.
Thank you. Okay. It's the talk on AI, so this is where everybody gets to talk about AI in the conference. Any questions here? Got it, okay. Yeah.
It's actually more of a suggestion, and Brian and I have talked about this before. You know what would be really nice is to be able to take an FDS input file and using whatever intelligence, whether it be human or artificial, very quickly create a CFAST or zone model type domain, and then run dozens of CFAST calculations with your variations and heat release rates and that sort of thing. And you'd very quickly get a sense of, for a given fire, what types of temperatures to expect. So before you spend all the time and effort to really crank up that big FDS calculation, you may be able to do a lot of parameter variations using a simpler zone model, and you wouldn't have to spend extra time to create that zone model, right? You spent a lot of time making the FDS geometry. It would be really nice to just be able to spin off, CFAST and run those calculations. So I'm just throwing it out there. Anyone who wants it, please feel free to implement it. We don't have the capability at NIST to do it, but if there's any, if this would be something that could be done with, again, I don't know if it's artificial intelligence or just a clever algorithm, right? That would be great.
Let's say that in this way. The VTK file format I mentioned before has not been like a random choice because the very same training for the artificial intelligence can be applied to several software. Okay, so that could be another option to do. It doesn't matter where the data comes from. As long as at some point we generate VTK file format, we can train the artificial intelligence using that data. Okay, so could be another good option, like to avoid like the computational time at least.
Right. But isn't the objective to investigate a wide range of scenarios to try to determine which one is the most severe?
Yes.
Okay, so I'm just suggesting that maybe, with something like zone model, you can use that to narrow down the possibilities.
Okay. Yeah.
So really interesting. Glad to see some more AI being done in Fire. I guess the question I have is on the VTK that you're using. We're working on an output for FDS in that space now. And I was just curious, are you using the VTK HDF output, or are you using just a standard VTK? And do you know what kind of data format you're using? Like, is it the unstructured geometry type output or structured?
Yeah, I passed through the plotted 3D file format in FDS, and I converted that into the standard VTK file format, which has been then opened to Paraview. Because in FDS I was able to generate, let's say, one VTK file for each mesh, and there were like 8 or 10 different VTK files, and then I use a VTK library basically to merge them all together into one single results. Eventually, the simulation, the final VTK file is an unstructured VTK file format, and when basically there is a list of cells with the variables, the variables value inside of these cells.
Okay, thank you.
You're welcome.
Thanks, Ruggero. It's a very interesting talk. So, but I'm a little bit confused. Okay. So it seems to me that the comparisons that you showed, correct me if I'm wrong, like all of the AI predictions were exactly scenarios that you had already run. Yeah?
Yeah.
Okay. So it's a trivial comparison, right? I mean, in other words, you have, like, in those cases, you really already have the data. You've saved it.
Exactly.
Okay.
But they were not.
So what do I do with this AI? I mean, do you have any results where the AI is like trying to predict a fire, where then you ran FDS? Let's say you move. Okay, you had 24 different cases. Yeah, I think something like that.
Yeah.
Okay. Maybe you have a 25th case where you position the burner in a different HRR curve somewhere else. You run that CFD calculation, but you don't put it into the AI. Okay, and then you take the AI and you say, okay, I'm going to put these parameters in and then compare. Okay, that to me is a comparison.
But this is what I did. 2 cases were not passed to the artificial intelligence.
Okay,
so the artificial intelligence didn't see these 2 cases.
Okay.
The artificial intelligence saw only the remaining 22 cases, and these 2 cases were kept separately, and we made the predictions of these 2 cases with the artificial intelligence, and then we compared this prediction against the 2 cases that were performed.
Sorry, I missed that. Okay.
One more follow-up question. So so I guess in the scenario that you're working with now within this framework, is it possible to, so like when I was doing this in the past with CFAST and FDS, we were trying to build a model that would be building blocks. So you could have a simple model. We were doing like a 2-room, a 3-room type configuration, and then building the plumbing to do the prediction. But then saying, now I've got a 50-room structure, and I want to predict that. And so you train the model with the really simplified stuff, and then predict the really detailed model.
Yeah.
Is your framework set up to do that type of thing as well?
Currently, that falls within what I call the geometry variations of the model. Okay. I haven't implemented anything in this regard. I have 2 or 3 possibilities. One of the possibilities is that the geometry, once we provide the input FDS file, we already have the geometry in the FDS file. So we can provide that instead of expecting the artificial intelligence to generate the geometry, we can also pass the geometry as an input data to the artificial intelligence, and that probably is the easiest solution to do that. Another thing, there are some procedures available in libraries like TensorFlow or PyTorch that somehow, let's say, are able to make the geometry prediction, to use the results in one geometry to predict the results in a different geometry. Okay. I still haven't found a solution, a final solution to this, and for this reason I haven't implemented that. And I'm not showing that, but I mean, there are a few possibilities that I need to investigate in the coming weeks and months.
Okay, thank you.
You're welcome.
And I would, for the reference Kevin made about some conversations there, one of the big gaps we have right now between Pathfinder and Ventus and PyroSim or FDS is that in FDS, you're just defining obstructions to flow. And there's no sense of rooms, doors, you haven't defined spaces, you're defining just obstructions to flow. So you have to go through either you explicitly say this volume is a room and it's contained within these bounds, or you smartly figure it out from like,
Artificial.
yeah, I know.
I'll just put it into an engine.
Right. It figures out what are rooms and everything. So rooms, doors, mechanical ventilation, all these things that we use in like CFAST or Contam and Ventus, they sort of aren't explicit. So yeah, that would be an interesting tool or a feature, is to say, take this just obstructions to flow and interpret smartly volumes and boxes and rooms and connections, doors, that could be then mapped to all of the more simple models that have those explicitly defined. So anybody else? Oh. All right.
So did you consider, I mean, it's interesting that you did these 300-second snapshots, right?
Yeah.
Have you thought about playing with, if you'd have done 22 random times, what do you think the AI would have come up with in terms of then allowing time to be another parameter? And how hard do you think that's going to be to get the time dimension
as a parameter? It's going to be a little bit hard. We need probably to find a way to get the HRR curve as a dimensional in time. Okay, and so in this way, we can somehow reconstruct the transient behavior in whatever time frame we want. We would have to get the HRR dimensional, make our prediction adimensional in this adimensional frame, and then expand them into the time frame. That is the only solution I can see in this case.
Okay, well, I think with that, thank you very much.
You're welcome.
Great talk.